Alright, welcome back. Let us continue our logic slides. We will be on them for a while, but we stopped after getting some practice with all these different logical connectives that we've learned, and let's keep going with them. So please take a second to pause the video and see if you can do this one. So if I give you the values for P, Q, and R, what is this? What is the answer? So this is P ORed with Q, right? P ORed with this whole thing, right? Which is Q and not R. So see if you can figure that out. Is it true or is it false? So here's one way to figure it out if you're getting stuck. So I gave you P, Q, and R, but I know that those are false, true, and true, so let's replace them. So I got false ORed with true, ANDed with not true. Okay, so let's work on the inner stuff first. So like not true, what's that? If you have a not, you negate something. I had true and I negated it. Well, the answer is false, right? So this becomes false. Does that make sense? False ORed with true and false. All right, let's do this one. True ANDed with false is, well, true ANDed with false, so the answer is false, right? The only way to make true when you're ANDing stuff is if they're both true. So this now becomes, this whole thing's false. False ORed with false, and oh darn, that's the only case in inclusive OR where you get false at the end. Darn. Every other case would have led to true. But nope, we're ORing together, false and false. Well, the answer is false. There is no truth to be found. So F. Okay, so the answer is false, and that is why. Please yell at me. Come to office hours, come to the tutorial center if any of that is not making sense. Right? That's how it all works. So we used truth tables to come up with these. Let me show you now how to build your own truth table, because maybe one day you'll need one. So let's make the truth table for just generic P or Q and not R. P or Q and not R. So let's do that. Let's make a truth table for this, regardless of what P, Q, and R are. Let's have a case for all of them. So I don't know, maybe next time it'll be like true, false, false or something. Let's make our truth table. Okay, so I guess, yeah, I'll get to all this after I start building it for you. So this is what we want to end up with. We want to find the truth output for P ORed with Q and not R, and so we kind of like want that to be on the right side eventually. That'll be at the end of our truth table, but we need to get there, right? We need to build this final answer for P or Q and not R from individual pieces. So what are the pieces, right? It depends, like the answer, right? Depends on what P, Q, and R are. That could be true, false, some combination of those, right? So on the very left side of your truth table, you put all your variables, P, Q, and R, and you give all the possibilities for those, because those will lead to the answer for the final thing. So that's the very first thing you do. You put all your variables on the left. This is just the standard way of doing it all. Okay, so these are your variables. And they can vary, right? They're variables. So what in the world can P, Q, and R all be? You save the final column for what you're actually trying to get at, and then everything before it's intermediate. The first stuff is the variables, and there's a special order for those, just so that everybody's agreed on. The final variable column goes true, false, true, false. Like it alternates just like this. True, false, true, false, true, false, true, false. There's got to be 8 options. See if you can figure out why when there's 3 variables. So that's the final variable goes like this, and then the Q, the next variable, also oscillates, but it oscillates a little slower. So it goes true, true, false, false, true, true, false, false, true, true, false, false. This is just the standard order that everybody agrees on. True, true, false, false. And then finally, the original, the very first one, the very first column to the left of that, it oscillates even more slowly. So it's got 4 trues, then 4 falses. And I'd keep on oscillating 4 at a time if you needed more than that. True, 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 true. False, 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 false. So this is the order that you should give your variables in when you're making a truth table. Okay? So yeah, you're just alternating every 2 to the c rows, starting with c equals 0. So alternating every 1 row, every 2 rows, every 3 rows, or sorry, every 4 rows at the end. Every 1, every 2, every 4. Powers of 2. All right? So there's 8 options, right? P, Q, and R that could either be true or false. So it's 2 to the third option, so 8 total. And that's a good start, right? Secretly, this ordering is just binary. It's counting down in binary. We'll learn that later. So, all right, we need P, Q, and R. Eventually, we need to build P or Q and not R, but that's kind of like unwieldy. That's like a lot to like go through and look at in truth tables. So next we put intermediate stuff. So like I'm eventually going to need the value for not R to build the answer for all of this. Let's make a little row for just not R. And then same for, once I have not R, I can AND it with Q, and then I'll have my Q and not R. You see that? So every intermediate thing can go next. So I'll have the not R, I'll have the Q and not R, and I'll show you how easy it is to get at those. So those will be my intermediate stuff. Intermediate. Okay. So what is not R? This is just reading off a truth table now. So what is not R when R is true? What should go here? Well, it should be false. See that? Just read it off the real truth table for negation. All right, what is not R here when R is false? All right, it's true. All right, so this is going to be false, true, false, true, false, true. So now I have not R. And now I can easily make the Q and not R part, because I have not R here. I just need to AND it with the Q, which is over here. And I'll have the answer for what should go in this column. You see that? That's how you make it easy on yourself. So what is Q and not R? You take Q, you take the not R, you AND them together. What's true ANDed with false? Look at the truth table, it's false. What's true ANDed with true? Ooh, that's true. False ANDed with false. And so you just read it off. And so this will be false, this will be false, this will be true, this will be false, this will be false. All right, and then let me just check my notes to make sure that I'm not doing it wrong. And then finally, once you have all these things, you see how now you have Q and not R, you have P over here. The next thing is just OR them together, you have what you're looking for. So this is your final thing, it goes at the end. P ORed with Q and not R. This is your final thing. Does that make sense? So the final column is saved for the final operation you're trying to get at the very end. And now you can really easily get the answer because you just, all right, here's my P, here's my Q and not R. I need to OR them together. All right, so this is obviously true. I need to OR these two together. True ORed with true. Oh, that's true. I need to OR these together. True ORed with false. Oh, that's still true. And then you just keep going. That's true. This one's false. This one's true. And the rest of these are false. Okay? So, if you make the truth table, you can take any of these. False, true, true. Okay. Just read off the answer. False, true, true. Okay. The output is false. And now you have all the other 7 as well if you need them. Okay. So that is the idea. That's how you write your own truth table for whatever complicated expression you're trying to show. All right. You want to know all the possibilities for it. And that's how you write a truth table, and that's how you fill it in. All right? So please write a truth table for P and not Q using the same style. So write a truth table for this expression, all the possibilities, do it in this style. And assuming you gave it a good try, here's how you do it. So you got 2 variables in this, right? P and Q. So what could be P? What could be Q? You got the 2 options. So this could be, well, first of all, remember the pattern, right? It's true, false, true, false. And this will be true, true, false, false. Okay? And then I want to get at P and not Q. So like over here is P and not Q, but some intermediate step needs to be figure out what not Q is, right? Not Q. Let me redraw that Q over there too. Much better. So, all right, what's not Q from Q? Well, what's not true, that's false. What's not false, that's true. False, true, and then, all right, now I can build this answer very easily, right? I have my not Q, I have my P, I just need to AND them together. I get my answer. So what's true ANDed with false? That's false. True and true, true, false, false. So that is P and not Q. It's got a truth right there. And you can kind of read that from the only way it's true is if P is true and Q is false. You're kind of saying that when you say P and not Q. Can you read it from that? P is true and Q is false. It's the only way to make it true. We'll see that become more apparent later. But that's how you write the truth table. Hope you got that. Please yell at me as usual if it's not making sense. Let's next talk about implication or conditionals. All right. So the idea is we'd like to express if-then statements in math, and we want to make it very precise and cool. We want to be able to write in math like this: if A is true, then B must also be true. So that's a very common thing to want to express. We don't have that yet. So let's figure out how to make the truth table for this idea. It's called implication, okay? It's like a mathematical if statement. If A is true, then B must also be true. So people use arrows, either double arrows or single arrows for implication. And so this is like, you write it like this. So if P is true, then Q is true. And you could also say P implies Q. That's another way of reading that a bit quicker. Okay? And so let us express the idea of implication from like a normal everyday example, and then we'll talk about the truth table for it. So here's an example. Dad tells us that he will give, Dad tells me he'll give me $20 if I mow the lawn. Okay? And so this is an if statement. Let's express this in math. So let's say that P means I mow the lawn, right? Because that's like the thing that's required. And then Q is like the result. I get $20, right? P is I mow the lawn, Q is I get $20. And then so what Dad is essentially saying is P implies Q. He is claiming that if I mow the lawn, if this is true, if I mow the lawn is true, then Q will also be true. I get $20. That'll also be true. Okay? So if I mow the lawn, then I get $20. P implies Q. P arrow Q. Okay? So P is the hypothesis. That's the thing that has to be true. If this is true, under that assumption, Q is the conclusion. It's the thing that you can conclude to be true if the first thing is true, if the hypothesis is true. Okay? So P implies Q is if I mow the lawn, that's the first part. I mow the lawn is the P. Then, that's the second part. That's the conclusion. Then I get $20. That's the Q. Okay? Does that make sense? So you can break this down from this sentence by looking for things like, if I mow the lawn, that's the condition, right? The hypothesis. And then Dad will give me $20. That's the conclusion if I end up mowing the lawn. So it's kind of backwards in English, but you can put it right ways up, and that's how you express the idea. And then we want to figure out, like, is this a true or false statement, right? Is this true or false? What are the conditions? What are the outcomes? Okay, so let's come up with the truth table for this idea of implication, this if statement in math. All right. So again, P arrow Q. P implies Q. Yeah. P is I mow the lawn. Q is I get $20. Here is how you come up with the truth table for P implies Q. Like, all right, you have these options, right? All these options. Is P implies Q true or not? And remember that P arrow Q, P implies Q is this. If P, then Q. Hypothesis, conclusion. How do you know what to put here? And my secret, the way that I learned it, the way that I'll teach you, is you think of it in terms of like lying and telling the truth, or feeling cheated. Okay? So here are all the options for P and Q, as usual. They're just variables. When should P implies Q be true, and when should it be false? I claim that it should be false when you feel like you got cheated in this deal. All right? When it's unfair. That's the false spots. True every other place. Okay? So let's do it that way. Okay? So let's think about it in terms of that idea of feeling cheated if Dad lied to us or something. So if we mow the lawn, first of all, here are some ideas. Like, here's this first option in English. Like, P is true and Q is true. So I mow the lawn is true and I get $20 is true. Was the implication true? Was the if-then statement true? So if we mow the lawn and we get $20, then Dad was not lying to us, right? Because he's saying he'll give me $20 if I mow the lawn. So I did it. I mowed the lawn and I got the $20. So dad was telling the truth. He's like, yeah, if you mow the lawn, then I'll give you $20. I mowed the lawn, I got $20. It all worked out. So it should be true in this case. The implication should be true if the hypothesis and the conclusion are both true, okay? You can next ask, when should P implies Q be false? When would you feel cheated, right? When would you think that dad lied to you? And if you think about it long enough, it's this case. If you mowed the lawn, because that's P, right? And you didn't get $20, but dad said, if you mow the lawn, I'll give you $20. This case is the false case. Does that make sense? Because dad was lying. He was saying that P implies Q is true. It was a true conditional, but I upheld my hypothesis. I did not get my conclusion. I mowed the lawn. I did not get $20, but you told me that if I mow the lawn, I get $20. So that means you were lying to me. False. P implies Q is false if you're in that state. Does that make sense? And then the rest of these, we'll just say they're true, because dad was neither lying nor telling the truth in those cases. So, for example, if I did not mow the lawn, but I got $20 still, what does that tell me about what dad said? Well, it's kind of like null and void at that point, right? I didn't uphold my end of the bargain, but dad was still nice to me and he gave me $20. So I don't feel cheated. So that can be true here. We'll define that to be true if P is false and Q is true. The implication could be true in that case. And then finally, false and false. I didn't mow the lawn and I didn't get $20, but that's fine. I don't feel cheated because I didn't mow the lawn. I didn't uphold my end of the bargain. Does that make sense? So if they're both false, that's still true, right? The implication, the idea that if you mow the lawn, then I'll give you $20, that's still true. Dad wasn't lying to me. I just didn't mow the lawn. Of course I didn't get $20. The one case where dad was lying to me is if I mowed that lawn, but I did not get $20, right? That goes against everything that's right in this world, right? So that's the false case. It's only false there. That's when you feel cheated, okay? This is one of those ideas that just takes time to sink in, that might still be a little weird and vague to you. Just play around with it, read the book, do the exercises, and I promise it'll start making sense. Okay, so this is the one case where it's wrong, where you feel cheated, okay? So that's implication. That's what it means. That's your if-then in math. If you claim that it's true, then you must be in one of these three cases where it's true. Okay? You claim the if-then is true. All right. So with implication comes a bunch of other ideas. So let's talk about converse, contrapositive, and inverse, a bunch of definitions in math. That's usually going to be how lectures work in this class. I give a bunch of definitions, and we talk about the definitions. We give examples, okay? That's just how discrete math works. That's just how math works. All right, I promise it'll start making sense. You'll get used to it, though. So the converse of an implication. If you give me P implies Q and you ask for the converse of that, that's just you flip them. Q and P flip. The converse of P implies Q is Q implies P. You swap the hypothesis and the conclusion. That's all. So it's not the same. It's not equivalent, right? It's just a different idea. So swapping the converse of the example from the previous slide was, all right, if dad gives me $20, then I mow the lawn. That really is a different idea, right? If you think about it long enough. So that's that. That's the converse. Something similar yet different is the contrapositive. So the contrapositive of P implies Q is not Q implies not P. And this one's actually equivalent. Not equivalent to the converse, though. But these and this are the same thing. And you can prove that with the truth table. So what you do is you swap the hypothesis and the conclusion. You also negate both of them. And somehow that ends up with the same thing. So this is another way of expressing the idea, but it really is equivalent. So if dad doesn't give me $20, then I don't mow the lawn. That's how you would express it in math. Going from P to Q to the contrapositive, which is not Q implies not P. Okay? If dad doesn't give me $20, then I don't mow the lawn. All right? The inverse of P implies Q is just keep everything in the same order, but negate both. Negate the hypothesis and the conclusion. If I don't mow the lawn, then dad doesn't give me $20. It's a different idea, okay? Surprisingly, P implies Q is equivalent, it's logically equivalent to its contrapositive. It is not equivalent to its converse, and it's not equivalent to its inverse, but it is equivalent to its contrapositive. You still want these terms, though. They're still useful terms to talk about what if. What if this was true instead? Okay? The inverse and the converse, though, they're equivalent to each other, but they're not equivalent to the original statement of P implies Q. Okay? We'll talk about that more later, and we'll talk about how to prove those things later, too. Next comes, and finally, comes the biconditional. All right? The biconditional is double arrows. Ooh. P double arrow Q, called the biconditional. It's sometimes written like this, P-I-F-F, two Fs. It's a stronger if. P if Q. If it, we pronounce it, though, we don't just say P if Q. We pronounce it as P if and only if Q. So this idea from the previous lecture when I was talking about how to prove code correct, I said the word if and only if. I gave you a biconditional. All right, so that's how you say it. That's how you write it. P if and only if Q. P if and only if Q. The biconditional is a very strong form of implication. It's equivalent to the arrow in both directions. All right, it's equivalent to the arrow in both directions. It's equivalent to P implies Q and Q implies P. And you can get really technical, and I always get this mixed up, but you can break it up into the if part and the only if part. Let's see here. This one's the if. The if is when you go backwards. That's the if. And the only if part is when you go forward. So technically implication could also be said P only if Q. It's really weird, but that's how it works. This is the if, and this is the only if part of P if and only if Q. If you needed to break it down, that's how you do it. I will never test you on that, though. It's a little weird. Okay, so yeah, the biconditional is when you need two things. You want to claim that they are equivalent to each other. They match, okay? That means their truth values correspond. They're either both true or they're both false. Because it's equivalent to this, you can actually build out the bigger truth table to prove this all. But here is the final answer. P if and only if Q. If they're both true, the answer is true. If they differ, it's false. But if they're both false, it's still true because they agree, right? They agree. They're equivalent. Still equivalent, but they're true this time. Still equivalent, but they're false this time. It's true. The answer is true. Because the question was, are they the same? Does that make sense? So their truth values correspond exactly. That's what it means to be true in the biconditional. All right. Technically, this is the opposite of exclusive OR. You do the exclusive OR and you negate. That's another way to create the biconditional. Isn't that cool? So it just means they agree. It's true when they agree. It's okay if they're both false. It still means they agree. And so if it's the opposite of exclusive OR, then P if and only if Q is logically equivalent to first do the exclusive OR and then negate. Hoo-hoo. So those are the same. Another way to write the same thing. All right, so that's the biconditional. If and only if. Now let's talk about how we can prove that these things are the same. There's some laws, there's some rules that you can use to get all this stuff a bit quicker. All right, so let's talk about them. Of course, we have definitions first, though. That's how this works. So, all right. If you have a big proposition with a bunch of stuff combined with all these operators, you can call it a tautology if the proposition is always true in every single column of the truth table. So a tautology is when the answer is always true. So P ORed with not P, for example, that's called a tautology, because if you make a truth table for that, what's P? Well, it could be either true or false. What's not P? Well, if it was true, it's false. If it was false, it's true. If I OR together those things, P ORed with not P, P ORed with its own negation, it's like, all right, true or false? Yeah, one of those is true. The answer is true. False or true? Yeah, one of those is true. The answer is true in all the cases. That's called a tautology. Okay? Always true. This is kind of saying nothing, right? Does that make sense? It's just, you can replace it with truth, right? It's a tautology. It's always true. Likewise, you can make a contradiction as well. a proposition is a contradiction if it's always false in every column of its truth table. So P ANDed with not P, for example. Again, we know how to make P, we know how to make not P from P. True, false. False, true. If we AND those together, P ANDed with not P, well, one of those is always false, right? So the answer is going to be false always. False, false. That's a contradiction. It's never true. You see that? Never, never, ever true. That's the opposite of a tautology, kind of. And then finally, you have logical equivalence. Two propositions are logically equivalent if they always have the same truth value. Either they're both false or they're both true in every column, right? So equivalence, if you're trying to check if two things are equivalent, it's the same as checking if they're biconditional is a tautology. And I'll tell you what that means in a second. So let me show you this. So for example, not P ORed with not Q is equivalent to first doing the AND, P AND Q, and then negate that. That is logically equivalent because they're going to end up having the same truth value in every column. So it's just two different ways of saying the same idea. Let me prove that to you. So P, Q, we have true, 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 false, false, true, false, false. Well, I'm going to need not of both of those. I'll have, well, let me just do it fast. Let's do not P ORed with not Q. I promise you can do it all out. And then let's do the not P and Q. And I'll prove to you that these are the same thing. So what's not P? That's false. What's not Q? That's false. Or them together, still false. So let me do that faster for the rest of these. So that's going to be false ORed with true, true. It's going to be true ORed with false. So true, true ORed with true, true. All right, and then we have P and Q negated. So true ANDed with true is true, but negate that, it's false. True and false is false, negate that is true. False and true is false, negate that's true. False and false is false, negate that it's true. So look at how these all match. Equivalent, 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 equivalent. That means these are the same. These are logically equivalent propositions. They're written differently, but they're the same idea. And so another way of saying that things are logically equivalent is take them both, do a biconditional with both of them. So like do R not P ORed with not Q, do a biconditional with P and Q. And check this. Is it true that not P ORed with not Q if and only if not P and Q is true? What is that answer? So the idea is biconditional, it's true and they agree. False and false agree. So the answer is true for the biconditional because that's the outer logical operation. True and true, they agree. True and true, they agree. True and true, they agree. So this is a tautology. That's another way of saying that these things are logically equivalent. If you take a biconditional with them, do they agree in every case? Well, if they agree in every case, it's true in every line. If it's true in every line, it's a tautology. All right? So you can prove that two things are logically equivalent either by writing out the truth table, seeing if they correspond, or forming their biconditional and doing one if and only if the other, and seeing if it's always true. That means they always match. That means it's a tautology. Okay? There's a lot going on there. Your turn. So use a truth table to prove that P ANDed with not Q or Q is equivalent to just saying P by itself. Isn't that neat? So try this. Make a truth table. For this, you'll naturally need P anyway. See if those columns agree. Now here's how I'll do it. True, 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 false. False, true, false, false. Let's see, I'm going to need not Q. I'm going to need not Q ORed with regular Q. And I'm going to need P ANDed with all that. P ANDed with not Q ORed with Q. Whee. And the more of these you do, the faster you'll get because you'll learn the patterns. All right. So not Q is false. true, false, true. If I OR together, Q and not Q, one of those is always true, right? And the other's false. So you OR anything with a true on one side, the answer is true because it's inclusive OR. So this is a tautology, so it's kind of useless information. Get rid of it. If you and all that with P, right? P, and if you and something with true, it's always whatever this was. If it's false, it's false. Or if it was true, the whole thing's true. That's a little trick that you'll notice if you do this enough times. So like, all right, if this is true, if I'm anding with true, it's just like whatever this side was. True and with true, true and with true, false and with true. Oh, that one's false. It makes the whole thing false. If there's one false, it all goes away, right? So yeah, notice how this is the same as this. So they were equivalent, logically equivalent. And that's how you prove it. That's one way to prove it. Okay. Next, we have some laws to make this a bit faster so you don't have to go to a truth table every time you need to prove something. The first are called De Morgan's laws. They tell us how to, let's say, push a negation inside some bigger expression. So here's the idea. If you give me the negation of P or Q, I can push that negation inside, and this is logically equivalent to not P anded with not Q. You push the negation inwards, like it applies itself to P and Q, and also this gets flipped. The OR becomes an and, the and becomes an OR. If I negate P and Q, I push that negation into both of these, so I got not P and not Q, but the operator flips. The and becomes an OR. So, not P or Q becomes not P and not Q, and then the negation of P and Q becomes not P or not Q, okay? It doesn't matter what P and Q are. They could be like bigger expressions. This could be like a million lines long. It could be like X anded with Y, not Z, blah, blah, blah. And Q could be huge too. No matter what, they're eventually true or false, so just keep following the rule, all right? So here's an example. Let's simplify this big statement using De Morgan's laws, and let's consider it simplified once the negation is right next to the variables. Okay? So, first of all, you gotta like figure out what's going on here, like follow all the parentheses. Let's first push this negation inward, and notice what's happening. It's like the negation of all this thing. What's this whole thing? Well, it's this entire quantity, and this entire quantity ORed with this entire quantity. So if I'm negating, if I'm using De Morgan's law, boop, 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 this is my P, this is my Q. Do you see that? This is my P, this is my Q. And then I'm applying this De Morgan's law. So I'm going to bring in that negation to both of these, and I'm going to AND this. It's going to become an AND. So this becomes this whole thing, but negated P. So the negation of X ORed with not Y, right? Whatever that was, it just keeps on being there. And then I flip this OR to an AND, then I have the negation of Q. Negating this whole thing, not Z, ANDed with W. All right? So that's that. And then I can push those. Now I have these negations. I can push these inwards once more. So I'll push this negation inwards. Boop. And I'll push this negation inwards. And I'll end up with this. So this left side is one application of De Morgan's law, the same one again, right? So I'm going to end up with the negation of this. The OR becomes an AND. And then I have a negation of a negation, right? Not Y. That's what's going on there. So that's that side, and then I still have this AND. Then I have the De Morgan's law, which was this one on this whole thing. Push the negation inward to both sides, flip the AND to an OR. So this becomes not Z. The AND becomes an OR, and then it becomes not W. Okay? So that, I believe, is everything. And we'll see later that you can simplify two negations, these double negations. They just go away. Go away to nothing. So it's really not X and Y. And this is just Z or not W. But that's a different law. We'll talk about that later. Okay? So yeah, it's always they flip. So this OR becomes an AND, this AND becomes an OR, and we also bring in the negation to everybody, to both sides. All right, those are De Morgan's laws. They will definitely make our lives easier. And here's De Morgan. That's the dude's last name. I forget his first name though. So yeah, laws are useful because they can end up giving you much shorter things. Like you can use a law to prove that this is equivalent to P, then you only have to work with P for the rest of your computation. So much so much nicer. Okay, so those are De Morgan's laws. Let's next talk about just all of the laws, right? So there's a ton of equivalences that are useful. Some of them are named after people. Other ones are just, they have a name, but not after a person. Just useful enough to write down. Okay, so your book has a giant list. I have recreated the list for you on these slides, and there's just a bunch of equivalences. Every time you see one side, you can replace it with the other side, and everything is still correct because they were all logically equivalent after all. For example, there's equivalence that allows you to get rid of an implication. P implies Q is logically equivalent to not P ORed with Q. You can prove that with the truth table once and for all, and then you can start rewriting stuff. This is just an equality at that point. Okay, here are your laws. We got idempotent laws. If you OR P with itself, it's just P. If you AND P with itself, it's just good as one P. You don't need to have two. Associative laws, you can change where the parentheses are if there's a bunch of ORs. Or if there's a bunch of ANDs. You can change where the parentheses are. Commutative laws, you can flip P or Q to Q or P. Nothing changes. Same with AND. Distributive laws are kind of cool. You can distribute this P OR with Q, P with R, and the AND stays the same. That's kind of nice. Same with AND. AND can also distribute over OR. Kind of brings it inside. Just follow the rules. It'll all work out. Here's our double negation rules. Not P becomes P. And some things that we kind of have learned by doing truth tables. Like if you OR with true, like you're just getting true. If you AND with true, that's as good as the thing on the left. Like if it's true, it's still true. If it's false, it's all false. All right. So that is the idea there. You got your De Morgan's laws, of course. Some of these come from math, though, like you've seen them before. For example, associative laws, like those are things you've seen before. That's like plus is associative, the plus operator. This is no longer logic, but like 2 plus 3 plus 5, you can move those parentheses to be 2 plus 3 plus 5. You can do this other plus first. It's fine. It doesn't change anything. It's the same for AND and OR. Okay? Commutative laws, you've seen those before, like 2 times 3. That's the same as 3 times 2. That's the commutative law of multiplication. It also exists for addition. So you've seen these things before, but they also work in logic. It's interesting that distribution works like this, because like, what is it? Multiplication distributes over addition, but it doesn't work the other way around. This one works the other way around for AND and OR. Either way works. They both distribute. So here are your rules. Here are your laws. You'll be using these a lot. I don't know. Let's go back to this one. I can show you that these are the same, and like somebody came up with that rule, and then you can just write it down. Conditional identities. That's true. Here's your biconditional. It becomes those two implications added together. You just prove that once and for all, and then you're good to go. So for example, let's prove that this one works, and you'll discover why it's a law. Okay? Let me prove that these two are equivalent, no matter what P and Q are. In every case, it's always the same, so they're equivalent. They can be interchanged. They are interchangeable, I guess I should say. All right, so P, Q, true, 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 false, false, true, false, false. What is P implies Q? Well, that is the only time it's false is if you upheld the hypothesis, but you don't get the conclusion. No $20 for you. The rest of the time it's true. And then I need to show you that that's equivalent to not P or Q. So let's have not P first. So we'll use that. And then not P ORed with Q. So false, false, true, true, and then take this and OR it with Q. So we got true, false, true, true. And what do you know? That is the same as that. So they're equivalent and they're interchangeable. We've just proved that that law works, that it is a law. Okay? So with that in mind, you can just like rewrite one thing to another thing, maybe simplify it. Try to prove, use the laws to prove that P and Q implies P is a tautology. How do you prove that something's a tautology? Well, first of all, you could write the truth table out, but I want you to use the laws instead. What does it mean to be a tautology using these laws? It means that you can simplify the thing. This whole thing becomes just true by itself. It's always true, right? And then you should name each law that you use. All right? So you're starting from P and Q implies P. You're going to rewrite that using your laws. And you're going to eventually end up with just true. Okay? So try that. Use these laws on this slide. See if you can come up with the answer. All right. So yeah, let's work on this. When you're stuck, the best way to work is to always just transform it to and, ors, and nots, because a lot of these are made up of ands, ors, and nots, and not implications, right? There's no other implications anywhere else. So let's get rid of that implication first. So any implication becomes, P implies Q becomes not P or Q. We have proven that. So, all right. This is the left side, that is the right side, not this, ORed with this. This becomes not that whole thing, P and Q, ORed with the right side, which is P, right? And that's the idea, and that was, name the rule, that was called the conditional identity. I will abbreviate I don't know. And then we can push this negation inward with the De Morgan's rule, can't we? So this is what we would like to do. We get everything next to everything else. That's a good thing to do. Always push your negations inwards after you've gotten rid of your implications. That's one way to prove all this stuff. This will become, what? Not P ORed with not Q, right? That's the way De Morgan's works. This becomes not P, this becomes not Q. The and flips to OR. And then the rest is the same, ORed with P. Okay? That was a De Morgan's law. De Morgan. And then, we have to stare at this for a while. And you'll notice that we have a bunch of ORs, so that's cool. And then we have a P and we have a not P. That's going to end up being important. The rule that we can apply next will end up being this one. P ORed with not P is true. And so I need to get the P next to the not P together in parentheses. And I need to like shuffle things around because of that. All right? So eventually I'm not going to require you to say like, oh, I'm using the associative law. Oh, I'm using the commutative law. Because it's just kind of obvious that you can do those things. Like, you don't think about it when you do it for math, right? But right now I'm forcing you to do it. I need you to show that you are understanding all these laws. So I need to get the P and the not P next to each other. And so I need to, like, let's swap these things. Let's make this not Q ORed with not P. It's kind of closer now. That was a commutative law of OR. Okay, I use this one. I use the commutative law. Commute law, let's say. And then I still want to apply this rule, right? I want to eventually get to P ORed with not P. So I need them in that order. So I need to move stuff. I need to get the P and the not P next to each other. So let's use the associative law to change the parentheses around. Let's go from, I have it like this, but I want it like this. Okay, so that's an associative law of OR. That will become not Q ORed with, not P ORed with P. That was an associative law. And now I'm almost ready to apply this rule. I know it's commutative, but I need to do it to get the P on the left and the not P on the right. That's what this rule is saying. So I want it to look like that. So it's not yet ready. I know it's very tedious and silly, but there's a reason we're learning all this stuff. So I want to flip those two. Flip the P and the not P from here to here. That's it. Another commutative law use. All right, and then finally, this matches my rule. It matches my complement law. If you have something ORed with its negation, it goes away to true. So I have not Q ORed with, this all becomes true. That was the complement law. All right, and then finally, if I have something and I OR it with true, the whole answer is true. That's called the domination law. All right, so that's the answer. Hopefully you got something close to that. That's what I'm going to be expecting of you in your homework, okay, to do this kind of thing. So please, as usual, yell at me if you're having any trouble, if it's not making sense. All right, so that's very useful to be able to simplify your stuff. Sometimes, and like also we use truth tables, sometimes you want to do the kind of the opposite. You'd like to go in reverse. You'd like to, like somebody gives you a truth table and they're like, I don't know what this is. What is this formula? Well, let me show you how to go from a truth table to a proposition. Okay? There's a trick. You can immediately turn it into a proposition. It'll make you so cool. Okay? So the trick is to extract all the true cases. There's also a trick for extracting the false cases. I think you'll be able to extrapolate once I show you the trick for the true cases, but that's the one I'll teach you, okay? So extract all the true cases. Like, I don't know what this is. I'm going to make up the proposition for it. Where is it true? Here and here. See that? Forget about where it's false. Care about where it's true. All right, and then you think about when it's true. What are the conditions under which the answer is true? So, all right, it's true when P is true and Q is false. And it's also true when P is false and Q is true. If you take what I just said and write it down using our logical rules, you have made the formula, all right? So if your mystery proposition is true when P is false and Q is true, that's this case, P is false and Q is true, then you should add that idea. P is false and Q is true, not P and Q. All right, does that make sense? So this becomes, let's see here. This is P is false and Q is true. This one is P is true and Q is false, not Q. You see that? And then the trick is, once you've identified those things and you've come up with these, if you just OR those together, that's the answer. Let me show that to you. So the final answer is this whole thing, P and not Q, ORed with not P and Q. And that gives you this truth table. That gives you the formula. Yes, I know it's exclusive OR, but that's besides the point right now. Okay? So let me show this to you. You just extrapolate, or you extract the true cases. You come up with a formula for this one true case. Well, it was true because P is true and Q is false. That's how you represent that, P and not Q. And then this one was true when P is false, not P, and Q is true. So just Q, not P and Q. OR them together, you've made the truth table. Let me prove that to you. Here's P, here's Q. True, 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 false. False, true, false, false. All right, so, I don't know. Should I do this? Yeah, let's do not P. And then I'll show you not P. Let's do it in order. Let's do not Q first. because that'll allow me to do this one, P and not Q. And then I'll show you something interesting that happens there. So here's not Q, it's false, true, false, true. And so this one now is true and false, false, true and true, true. And the rest are false. So something very interesting happened when you made this particular formula. Same works for this one. It gives you a truth table where there's only one thing that's true. You see how this formula picks out when P is true and Q is false. You see that? When P is true and Q is false, P and not Q is true. It's false everywhere else. That allows you to pick out that one row of the truth table. And then we'll do the same for this one. Not P and Q. So what's not P? That's, well, false, false, true, true. And so not P and with Q, that represents when P is false and Q is true. It's going to make it true. So, all right, false ANDed with true. False. False ANDed with false. Still false. True ANDed with true. Ooh, true. And then we have false ANDed with true. So, or true ANDed with false. So it's false. These two things together this one and this one, they pick out exactly when we wanted them to be true. It's false everywhere else. This is true only right there. False everywhere else. This is true only right here. False everywhere else. If we ORed these together, we get, right? We get a truth table where it's false everywhere but those two places where it was true. Do you see that? That's the answer. So the final answer is that question mark. What should that have been? Well, it's P and not Q, ORed with not P and Q. And that's how you come up with it. Okay, you extract all the true cases, come up with when it's true, or together those little sub-propositions. All right? Alternatively, you can do the same for the false cases, do the same whole thing, and because you want it to be false in those cases and not true, you'll do the pattern, then you'll negate the whole thing. Use De Morgan's law to push it inwards. So, yeah, that's how it works. And then you've come up with this. I know this is exclusive OR, so it better simplify to that eventually. But now you have something to simplify. Okay? You're not just scratching your head. So that's how you come up with a proposition from a truth table. Not too bad. So please try that with this. What should this question mark be? Did you figure it out? So, you extract the true cases. So it's true here and here, don't care about anywhere else. So immediately I can read off the answer. This is true in this case because P is true and Q is true. P is true and Q is true. That's how you represent it, just like that. All right? And it's true in this case because when P is true and Q is false. P is true and Q is false. So it's true either then or then, in either case, so or. That's what the question mark should be, all right? Make the truth table for this if it doesn't make enough sense. I promise it will eventually. All right, you gotta definitely try these. So that is the answer, okay? So I just want to give you a sneak peek of what we're going to be doing next time before I end the lecture. But let's talk about one last concept called quantifiers. Fancy term. So it also has to do with something called a predicate. So we've talked about propositions, right? Propositions are things that are true and false. Predicates are things that can become propositions, but they're not yet propositions. A predicate's a logical statement whose truth value is a function of one or more variables. Okay? So you apply the function and then you end up with something that could be interpreted as true or false. Okay? It's not yet true or false. This will make sense with an example. So here is my proposition. Let's define the proposition P that takes variables x and y, takes parameters x and y. Define that to be x loves y. So the proposition Pxy is true, define it to be true whenever x loves y. Okay? So this is a fancy mathematical symbol. You'll see it. So equals with a dot over it is equivalent to equals with the word def over it, which is equal to just, it's a definition. That's what it means. Mathematicians are very precise. So this is the predicate P. I'm defining it. It takes two arguments. It's defined to mean x loves y when you apply it to those things. So P of Lawton and cats is true, right? Because Lawton loves cats. You see that? Now it's a proposition. Now it's true or false. All right? But this is not true, and it's very unfortunate during the pandemic. So I do not like the smell of hand sanitizer. So P of all this, P of Lawton, the smell of hand sanitizer, the negation is true, okay? It's a false statement otherwise. Does that make sense? So P by itself, it's just the idea of somebody loving something. It's not yet true or false because it's like, maybe I love cats, but somebody else doesn't like them. And they are wrong, of course, but you can express that idea in logic. Okay, so that's a predicate. Next, we have domains, all right? Domain is a set of possible values for the variables in your predicate. You can think of them as like the types of your predicate variables. Kind of like mathematical types. All right, so for example, if you define this predicate, P of x, define it to be this idea. So given an x, check if x minus 3 is greater than 5, then what's the domain? What are all the values that P works on? Well, how can you use P is the question. Like, all right, you can give it 42. You can ask, that asks if 42 minus 3 is greater than 5, right? True or false? P of 0, you can ask, so like every integer, that's in the domain of x. But you could get fancier, like you could ask for P of pi. You can ask for P of 2 pi. So you can also define the domain to be every integer multiple of pi. Like that's the only things that I want you to be able to use P on, right? But it all depends, right? You cannot apply this P to a person. Does that make sense? Because the right side makes no sense when you do that. So you need a domain. You need like a type for your arguments of your predicate. But it can be anything. Like all the integers is like you can apply it to 42 and 0. But if your domain is the integers, that means you can't apply P to pi yet. Maybe you wanted pi. So you can say that the domain is, all right, it's every integer multiple of pi. That's another way. I think this is a better way of me going through it. So you can say, all right, you can apply it to P of pi. You can apply it to P of 2 pi. You can apply it to P of negative 4 pi. You can apply it to 0, because what's 0 but 0 times pi? But you can't apply it to, I don't know, 42. It doesn't work because that's 42 is not an integer multiple of pi. So the domain of your predicate tells you what things you can ask, is it true or false for, okay, etc. This is called a domain restriction, because usually you just want it to be every possible number, right? This is a restricted domain. So you can ask, what now is the domain of this P, this predicate P that takes two things? Where do I want to write this? Let's write it up here, I guess. So actually, it's not the domain of P. You can say it P here because it only takes a variable, but really it's the domain of its variables, of its arguments, of its parameters. So what's the domain of X? And what's the domain of Y? That could be two different domains. So maybe I only want to ask the question about somebody loving something if like X is a person, like only people can love things. Don't put anything else for X, only people. And then Y is just anything that could exist, like any noun. Okay, so that's how you can create the domain and define it for a predicate. You cannot use it in any other way, all right? But a predicate is just kind of like a function that takes things and gives back true or false once it took those things. It needs something concrete, because like only somebody can love something, but people sometimes don't love certain other things. So it depends on the things, and that's why it's a predicate. It's not yet true or false, you have to apply it, okay? And then the things that you could apply the predicate to, you can restrict those to be part of certain domains. Think of them as types, okay? So those are predicates. We're going to get really fancy with those next time, okay? So that'll be the end of this lecture. I'm going to split up the lab introduction lecture from main lecture. So like I'm putting this video that I'm recording right here and here in this lecture 2 link. Lab 0, also going to come out this week. I'm going to go and record that video separately and it will appear here. Okay, so that's how it's going to work. So please next go to the Lab 0 page and start the lab if it's out. Okay, so that's how the week, your standard week will work in this class. You'll go through the lectures, you'll click on the labs, and there will also be lab introduction videos there too. Okay, so that's what I will record next. So I'll see you there.